Yes, recording is started. So as we have seen all the theories of failure and design procedure and all other things which are required that we can say as the basic things which are for the machine design. And also we have seen some of the parts related to the design and how one can go for the designing of any component, in which important thing is that creativity. And if we are better in creativity, we can go for the with much more better component designs, and we can survive the humankind by the better applications and better products also, and we can reduce the efforts of human being. Question is that where we are going to utilize that all remaining time which we are going to save when we are going to design any new component, or when we are going to have a component, new component, new product, new application. Now here we are going to start with the conventional one, that how the mechanical parts are designed. On screen you can see one, basically you might have seen such type of joints where two shafts are connected with each other. Now shafts always are not transmitting the torque, sometimes they are used in pulling also. That is, they are going to transmit the tensile load. And while they are transmitting tensile load, at that time, sometimes it is feasible to have the two parts of that shaft. Sometimes we can use single shaft only. But if the two parts are connected with each other, for that is nothing but we can take example of tractor and trolley, where drawbar pull is connected. Because that example we are going to have the daily example, we can say, where we can see it. Also sometimes in such applications where joints are used, they are elaborated by means of compressive and tensile load. And this compression which is coming in that joints is for the short time, whereas the tensile load is higher. Now here you can see uh, this is one point, and this tensile load is applied, whereas the second part where again tensile load is applied. These two parts are connected with each other. They are insert, this particular part is getting inserted or inserted this part, and this vertical part which you can see is called as pin, that has inserted between the two parts. Now this application or this particular joint is known as pocket and spigot quarter joint. Now this pocket and spigot quarter joint, out of that one part is called as pocket, second part is called as spigot, and this pin is called as quarter pin. So quarter pin is inserted, and this all joint is capable to handle the tensile load which is coming while we are going to join two various components with each other, two various parts of the machinery with each other. Little bit you can see the practical application of this. Let me check some of the applications of this quarter joint, that is sprocket and spigot joint. Let me check and share it. By the way, how many of you are knowing that this type of joint we have seen in actual, because it is very rare to see such type of joint nowadays. Their applications are very limited. That's why rarely we see such type of joints. Even in bicycle, have you seen that paddles are connected with the shaft while we are going to use, or while we are going to see the what paddle, and that shaft on the paddle is connected with each other. Over there also, one pin is inserted. That pin is also called as quarter pin, and that quarter pin is just what we can say has a taper shape, and that's why it is capable to handle the tensile or whatever may be the shear load which we are going to see there. Just I'm going to share one application. Am I audible?
Yes, sir.
Anyone? Okay.
Yes, sir.
Okay. 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 So just I'm going to check one application. Typical application of quarter joint. Okay, I'll share this screen, and we are capable to see it. How many students are joining late? Just wait, just wait, just. Are you able to see screen now? Hello?
No, sir. No.
Now?
Yes, sir.
Yes.
Yes, sir.
Yeah. Okay, here, whether you are going to see one application of quarter joint, which is used in steam engines. Now, slowly I will run this video. You can see it. Here, the red part, red circle which has been shown here is the application. This rod is connected with this hub by means of this quarter joint. Now this application is for the steam engines. Nowadays, this particular application also is used for the braking system of railways, and where up to suspension point this quarter joint is used. That's why I told you that it is very rare to see the application of quarter joint nowadays. It was initially widely used in locomotives as well as in ships also, but it has been replaced by means of nowadays knuckle joint, because knuckle joint is going to give us more degrees of freedom, and that's why its application is restricted. But till we are going to utilize it for the transmitting of tensile load, and it is going to give us basic idea about how the machine or components are designed. Are you able to see screen now?
Yes, sir.
Okay. We'll go further, and before going to detailed steps of design for the finding and finding the dimensions of this quarter joint, we'll see various parts which are there on the quarter joint. So the first point which we are going to see is the sprocket. Okay. Now here you can see the detailed drawing of this quarter joint. Out of that, this is the rod basically where we are going to transmit the tensile load. Here also, this same type of rod is there which is capable to handle the tensile load. Now this particular part is called as sprocket end. Now this sprocket end is made hollow inside, and This is called as spigot end. This spigot is inserted inside this pocket, and later on this quarter pin is inserted in this hole which has provided for the quarter joint. And hence what happens that this spigot and this sprocket is going to get locked because of this quarter pin, and it is sustaining the tensile load. If we are not going to insert this quarter in between this slot, then easily this spigot will come out from this pocket. Okay, there will not be any use of this joint. Now this, if you are going to see this quarter pin, then this quarter pin is made somewhat taper. Now you can understand why, because it has made taper, because if you are going to assemble it together, then easily by means of application of hammer force here, you can assemble this quarter joint. And if you want to dismantle it, just you have to hammer from the bottom side, and this quarter will come out, and you can disengage this quarter and sprocket and spigot. So you can easily make assembly of this joint. Also you can disassemble this joint easily. That's why this pin has made quarter, or this quarter pin has made taper. Okay, and that is for the easy assembly and disassembly. Now one by one, if you are going to see the part, this is called as quarter, and this quarter is made somewhat taper. Now thickness of this quarter is decided by means of how much load you want to transmit, and also width of this quarter is decided by means of that same force which you want to transmit by means of that quarter joint. Then this is what you are going to call it as a spigot. Okay, as here you mention it as a spigot. Okay, then this spigot is made of solid shaft, where we are going to make this groove for the quarter joint, and remaining part is kept as it is for the transmitting of tensile load, as well as it is capable to compressive load also. Now this collar is made so that we can restrict how much this quarter will, or this spigot will get entered or inserted in the sprocket. That's why this collar is made, and this collar also helps us to sustain compressive load also. Next, this is spigot, where the hollow part is made, inside which we can insert the sprocket, and these two holes are provided for inserting of the quarter. Here also you can see this collar is provided. This collar is capable to take tensile load. Okay, where at the spigot end you have seen the collar. These two collars are going to meet each other, and they are somewhat capable to take compressive load also, and they can transmit tensile as well as compressive load. But most of the cases, this specially designed of this quarter joint is made for the tensile load only. Very rare application, or for a very short time they are sustaining compressive load. Now one by one, if you are going to say the what is the description of this spigot, then sprocket and quarter. And this spigot is the male part of joint. It has rectangular slot for the passing of the quarter through it. As already we have seen, the rectangular slot is provided, and inside that slot we are going to provide the quarter. Okay, then spigot has a collar which rests against the sprocket end, which is going to restrict the transmission of that sprocket inside the spigot. Spigot inside the sprocket. Okay, now the sprocket is also made. It is a female part where we are going to insert the sprocket, and later on the holes are provided so that we can insert the quarter. The main part is the quarter, which is withstand to take the shear load, because most commonly the part which is going to fail inside this quarter joint is the quarter, because easily that quarter has to be failed so that we can replace that quarter instead of replacing spigot and sprocket, because they are more costly, and as compared to the spigot and sprocket, the quarter pin is cheaper. That's why it has made such that the failure will occur in case of quarter, and later on we can replace it. Though again the failure criteria has to be applied on the quarter, and we have to make such dimensions of that quarter such that it will not undergo to the failure. Okay. Then it has made taper also. So already I have mentioned you the taper is made on that quarter so that assembly and disassembly becomes easy. Now this is conventional drawing of this quarter joint. You might have drawn this particular thing while you was learning the machine drawing subject, where assembly and details drawing you might have drawn. Now here this drawing is not only showing the how that quarter joint is looking, but it shows the various dimensions. Now here you can see we'll start from the load apply. We are going to use this P as a convention for the applied load. Then second point, we are going to consider d, small d, as the diameter of rod. Now these rods are kept of same diameter to the spigot end and to the this sprocket end too, because they are sustaining same amount of this tensile load. Okay. Next, when we are going to see this pocket, the collar diameter of this pocket is considered as a D3. Whereas the part which we are going to insert in the spigot of this pocket, that is having somewhat higher dimension, and that you are going to mention as a D2 dimension. Diameter of that inserted part is D2. Okay, so D is the rod diameter, D3 is the collar diameter, D2 is the pocket diameter, you can say. Now this D1 is the diameter of the spigot end, that is outer diameter of the spigot, we are going to say it. Okay, whereas you can consider that this pocket, when it is inserted inside the spigot, this diameter D2 is also diameter of this, or inner diameter of this spigot pocket. Getting me? So this inner diameter of pocket and outer diameter of spigot is the same as a D2. So D, then D1, D2, D3. These are the conventions which we are going to use for the various dimensions on the sprocket and spigot joint. Now, how much part we are going to keep at the spigot end, where when load is applied, that is considered as a C, because this width is going to play a very important role while we are going to join these two parts together and tensile load is applied, because there may be possibility that this pocket may get shear because of this width. So that width we are going to consider as a C. Whereas thickness of this collar of spigot we are going to consider as a T1. Then remaining part of the spigot after the quarter, that you are going to consider as a dimension A. Then we are going to consider the outer diameter of sprocket as a D4. And now if you see the dimensions of quarter, width of this dimension or quarter is called as B. Just a minute. Are you listening me?
Yes, sir.
Am I clearly audible to all of you? Okay. So keep in mind that the abbreviations which we are going to use, the shortcuts which we are going to use for the various dimensions. Okay. Nomenclature of this quarter joint. It is also called as nomenclature. Nomenclature is nothing but the shortcuts which we are going to use for the various dimensions of this sprocket and spigot joint. Okay. So separately, if you are going to make a list of this all abbreviations or nomenclatures, we can clearly write D is the diameter of the rod which is used for the transmitting of that tensile load. P is the tensile load which is applied on this pocket and spigot joint. Then D2, D3 diameters, as well as A and C, as well as D as a dimension. One more dimension which is not shown in this diagram, that is the thickness of this quarter. It is denoted by T. Okay, so these abbreviations we are going to use for this quarter joint. And now we'll see here, I will make the separate list of these abbreviations. So P is the load, then D is the diameter of rod, D1 is the outer diameter of sprocket, D2 is the diameter of spigot, that is outer diameter of the spigot or inner diameter of the sprocket, D3 is the outer diameter of the sprocket, spigot collar, then D4 is the diameter of the sprocket collar, T1 is the thickness of the sprocket collar, and A is the distance from the end of slot to end of the spigot, C is the thickness of the sprocket collar, and B, T, L. B is the width of quarter, T is the thickness of quarter, and L is the length of quarter. Okay. Now, by means of using these abbreviations, we are going to do further calculation. That's why these abbreviations are very important. And when we are going to calculate various dimensions, these all dimensions we have to find out, except this load applied, P. P is the load applied. Remaining are the dimensions. These dimensions we have to calculate. And that you are going to call it as a design of the quarter joint or design of this pivot and sprocket joint. Now, how to calculate these dimensions? That is question. Now, which relation we are going to use for that? How we are going to consider the various load which is applied on this quarter joint? Basically, if you are going to see, they are designed only for transmitting the tensile load, and we are going to consider the basic load as a tensile load only. So when we are going to consider this all application of this quarter joint, then one by one we'll take all parts and we will calculate the dimensions of that part. Now we'll take first part, where it is called as first step of design. Now, it is very important to calculate first of all diameter of rod, because in conventional design procedure, you can refer this diameter or rod diameter and you can find the rest of the dimensions of this quarter joint, or you can make some proportionate also. That is nothing but you can make one standard procedure by means of which you can find easily the remaining dimensions. It is not always necessary to check the stress level, but if once you find the diameter of rod in proportionate of that diameter, you can calculate the other dimensions of this quarter joint. There is nothing but if the diameter D is used for the rod, then in terms of D, what will be the thickness of quarter, what will be the width of quarter, what will be the length of quarter, also what will be the inner diameter of the sprocket, what will be the outer diameter of spigot. All these dimensions you can write in form of rod diameter. That it will be 1.2 D, it will be 1.5 D, it will be 0.3 D, likewise. And that's why it is very important to calculate first of all diameter of the rod which is transmitting the tensile load. Now, we know one relation, that stress is equal to force divided by area. Now, while we are transmitting the tensile load by means of this rod, which area will be encountered by means of stress? Where the stress will get generated? Obviously, that all stress will be of tensile type. Now, this arrow is showing the application of load. Now, load is applied in this direction. Definitely, other type of load or other end will be applying that load in the opposite direction. So, when we are going to apply such type of tensile load, what will happen to this rod? It will likely to elongate. Am I right? And if that is within the elastic limit, it will, when we are going to release the load, it will regain its original shape. Diameter will remain same. But if it goes beyond the elastic limit, then dimension of that rod will get changed. Diameter will get reduced and it will get elongated. Length will get increased. That you are going to call as a failure. That's why the limiting stress value for this rod we are going to consider as a ultimate tensile strength. Okay, that ultimate tensile strength, that is nothing but limiting value where the breakdown is going to occur. But before that, if little consideration you are going to do here, then it yield point will come before that. So if the yielding is going to start, then also we can consider, or rather than at that point only we have to consider the failure of this rod is occurred. I'll repeat it once again. Before having the total breakdown, that means rod is going to cut in two pieces, yielding will get start, and that will start at the yield strength, right? Yes, y, T also sometimes used. So yes, strength, yes, y, T abbreviation we are going to use for it. Yes, y, T nomenclature we are going to use for that. Okay. So before that yield strength, if you are going to apply tensile load, then that is called as the safe design. But if you are going to apply load more than the yield strength, then we are going to consider as a failure is going to occur, or failure of that rod has started. Getting me? So now here one question, let me ask that which material you will be prefer for this rod, whether it will be brittle or it will be ductile material. Any one of you? Which material you will prefer for this? Hello? Am I?
Ductile material, sir.
Ductile material. Okay, Parmar, you will choose ductile material. Okay. Why you are going to choose this ductile material only? Aman.
Because it
Yes.
won't get break
It won't
easily.
get break easily. Okay, okay, no problem. Aman, Mulani, which material you will prefer for this? Hello? Are you listening me, Aman? Hello? Mulani, don't do such type of things. You are live on this lecture and you are not capable to view, or you are not capable to unmute yourself. Mulani, are you present there? Aman Mulani. Londe. Avinash Londe. Hello? Okay, let's continue. Anybody else? Can you give your opinion that which material you will use for this? Kulkarni,
Ductile, sir.
ductile material only. Okay.
Ductile,
Okay.
sir.
Ductile material. Right. Okay. So we'll use ductile material for this instead of going for the brittle materials, because they are more capable to sustain compressive load, that brittle materials, rather than the tensile load. That's why we are going to use ductile material for this, and we'll use this brittle material, that is cast iron, where we are going to have more compressive load rather than the tensile load. So when we are going to consider this rod, an area which is encountered by means of this stress, then here it has elaborated in this slide that which area is encountered by means of this tensile load. Now this rod is elongated. Okay, here it has been shown that which area for this, showing the area we have seen this red part. Okay, now this tensile load is applied, and hence this rod will get elongated and this area will get encountered. Now already we have decided that D is the diameter of that rod. Then what will the area? Easily one can calculate that pi by 4 D square and this sigma T, because when we are going to calculate this, sigma T is the tensile stress which has developed in this rod. Sigma T is equal to force divided by area. Now this area, that is pi by 4 D square, is taken to the one side towards the stress side, so that one can calculate how much P, that is the load, tensile load, can be applied, can be sustained by means of this rod. Now once you are going to decide this value P, let's suppose we are going to use this quarter joint for 100 kilonewton force which has transmitted, tensile force which is transmitted. Then this P value will become 100 kilonewton. Then we have decided which material we are going to use for this rod. This material will give this material property, that what will be the tensile strength of that material. The sigma T value will be given. Now how we are going to decide this sigma T? Again, whether we are going to decide as it is. No. The sigma T is calculated by means of factor of safety first. Sigma T value is calculated by means of factor of safety. And how that sigma T value is calculated? It is calculated by means of SYT divided by factor of safety. So what factor of safety you are going to decide for this rod? Depending upon that, the value of sigma T is decided. That is the tensile strength or tensile stress value will be decided. Design tensile stress value will be decided. This is not actual sustainless tensile strength. Otherwise, we might have written here SYT, that is the yield strength of that material. But we have written it as a sigma T, and this sigma T value is calculated by means of SYT divided by factor of safety. Now it is in designer's hand at how much factor of safety you are going to use for that. We are going to see it in details when we are solving problems. Okay. Now, here it is written that since area is resting is the circular, using the basic equation of design, load is equal to stress multiplied by area, or stress is equal to load divided by area, we can calculate how much load will be sustained by that rod, or what will be the diameter of that rod. This is mathematical equation only. So area of resisting for the tensile multiplied by allowable tensile stress. This allowable tensile stress is calculated as sigma SYT divided by factor of safety. It is written in mathematical form only, and from that you can decide this diameter of rod. From this equation, determine D of rod, that is diameter of rod is calculated for the given application for given tensile load P, okay, of given material. So here, once you have calculated diameter, that diameter is kept as it is, that you are going to use for the rod. Now step 2, design of spigot. Now once you have decided the diameter of the rod, then we are going to take next part for the designing or calculating dimensions as a spigot. Now spigot dimensions are there, that is D2 is the outer diameter, then D3 is the, D2 is the inner diameter, D3 is the outer diameter of that collar, T1 is the thickness of that collar, A is the width, which is towards the after the quarter. Okay, so it is also considered as a tensile failure. That is nothing but it is also sustaining the tensile load, and that spigot is considered under the tensile. Now this slide shows that how the tensile force is going to break that spigot. Now here also, if you are going to use ductile material, failure will occur before it get total fail. That is, elongation will start, and that will start at the yield strength. So yielding, once the yielding of the spigot starts, then we are going to consider as a failure of that spigot, and hence we are going to restrict the stress level up to the yield strength only. Above that yield strength, we are not permitting to have the stress. Again, we are going to use factor of safety, and sigma T value, that is the allowable tensile stress value, is calculated by means of formulae, that is SYT divided by factor of safety. Yield strength of that material divided by factor of safety. And hence, we can calculate sigma T, allowable tensile stress value in this figure. Now, when we are going to consider the failure is occurring in this tension, then which area will be encountered by means of this tensile load? That area is elaborated here. And definitely that area is not the pi by 4 d square, because slot is made here. This is hollow part, and it is not sustaining any type of load. It is just made as a hollow to insert the quarter. So how we are going to calculate this area? Definitely the area of this circle minus whatever may be this area, and this area will be the width and diameter. That is, this is width. So how much width you are going to keep here? That width will be width of the quarter, because here you are going to insert quarter. That's why this width will be exactly the width of quarter. And how much this length will be of this rectangle? This length will be equal to the diameter of this circle. Am I right? So while you are going to calculate the area which is restricting this tensile stress, that will be this circular area minus this rectangular area. And hence, here you can see, because this is going to convert into two pieces by means of shear. If it is shearing while sustaining the tensile load, then this area of this slot is the cross-sectional area of this quarter. Okay, such type of failure is going to occur in case of spigot. So that area is calculated as pi by 4 d square, that is d2 here we are going to use. D2 is the diameter of that spigot, minus T2, that is the diameter, multiplied by the T, thickness of that quarter. Okay, so this will become the area which is resisting to this tensile stress. So area multiplied by stress is the load sustained by means of that spigot, right? And hence, if we are going to decide the value of this P, that is 100 kilonewton, if we are going to calculate this sigma T by means of material property, that is SYT divided by factor of safety, then you can calculate this remaining dimensions. Now here one question is that D2 is okay, one variable. We can calculate it. This is one equation, and by means of this one equation, we can calculate this D2. But what will happen to this T? Or if D2 is known, T can be calculated. Here in this equation, how many unknowns are there? One is P. You can decide it, okay, for the given application. Sigma T, you can take from the material property. Then again, there are two unknowns and one equation. It is not possible to solve it. So what is done? This D2 dimension is calculated in terms of T. And later on, once you are going to calculate this dimension, D2, in terms of T, and if you are going to design the quarter, then this T is automatically calculated over there. That T value is inserted and diameter D2 is calculated. Okay, D2 can be find out. Okay, till now, am I making any sense? Do you have any question? Whether we are going right? Hello? Anybody of you? Are you getting, or I have to again elaborate it? Dhare, Rupesh Dhare. Who is there?
Yes, sir, we are getting.
Okay. So, we are going in the right direction.
Yes, sir.
Right. Okay. So once you are able to find out the diameter of that spigot, outer diameter of that spigot, then that is the same diameter for the sprocket. that is inner diameter of this pocket. Okay, so it is not necessary to find separately the inner diameter of that pocket. It is the same as the outer diameter of the spigot. Okay. Now, next thing we are going to calculate by means of arbitrary formulas or by means of what we can say experience. This D3 is the collar diameter. Okay, and that is called as empirical relationships. By means of these empirical relationships, we are going to calculate the collar diameter as a 1.5 of rod diameter. Already, I have told you that rod diameter is very important, based on which we can decide the other dimensions too, and we can make this design procedure somewhat simpler. Or otherwise, we are going to this total design procedure will become complicated. Okay, we have to go for each and every dimensions to find out. Okay, instead of that, this experience or empirical relationships are developed for this quarter joint, and these dimensions are calculated. Okay, so D3 is the collar, that is collar diameter, that is calculated as a 1.5D. A is the width where we are going to keep this towards the rod side of this pocket. Okay, I will show the slide where we are. Yes, this is the A dimension. That is how much part we have to keep inside the pocket, okay, of this spigot. So that is nothing but the A dimension we have seen, and this A is again calculated by means of empirical relationship with the diameter D. So this A is 0.75 of D. Okay, T1 is the thickness of that collar. That is, once you have found out the diameter of that collar, T1 is the thickness of this collar. Here you can see. This is the T1, thickness of this collar of this spigot. Okay, so this thickness of collar is calculated by means of empirical formulae, that as a 0.45 of D. Okay, so we have calculated all the dimensions of the spigot, and that D2 diameter which you have calculated in terms of T, that D2 diameter again can be calculated once you are going to find out the thickness of that quarter. Okay. Next, this is what we have considered as a tensile stress. But is there any other possibility that stress may occur in case of that spigot? That is the crushing stress. That is, while we are transmitting the tensile load by means of this quarter joint, there may be possibility that it may get crushed. That quarter may be doing crushing on that spigot. So that area which we are going to consider will create or will sustain the crushing stress, and this crushing stress are as good as the compressive type of stress. Okay, but we are going to, as the nature of load is crushing load, that's why we are going to consider it as a crushing stress. Otherwise, they are in simple way we can consider it as a compressive stress. So this compressive stress is calculated. This stress is calculated by means of SYT divided by the factor of safety. That is how much strength you want to give for the spigot in case of compression or in case of stretch. D2 is the diameter of that spigot. It is outer diameter of that spigot. T is the thickness of quarter pin. Because this quarter pin, and here you can see, this part will undergo to the crush. Are you getting me? Or in this case, this rectangle will create the crushing on this part. And as it is creating tensile load, that's why it will be apply compressive load at this point, at this junction. and that area will be this area of rectangle. And area of rectangle is calculated by means of d2, that is the diameter of this circle, multiplied by t. T is the thickness of this quarter where you are going to insert the quarter of this slot. That's why t. This T multiplied by d2, that is the area, multiplied by stress. So load is equal to area multiplied by stress, and hence we can just check that value of sigma c is within the limit or not. And once you find that the sigma t is within the limit, then we can say that the design is safe. Okay. Now this all we have seen for the compressive load. Now, what will happen if the tensile load is applied? And that tensile load is going to create shear of this rectangle which you are going to see here. See, as we are going to use this quarter, and this quarter is of having dimension of equal to this slot, there may be possibility that this quarter may slide this rectangle or this rectangular volume with the quarter, and this pivot may have the, or it may get slide to the other direction. So what will happen if it will get shear out? We have to restrict it. This shearing we have to restrict. And who will check it? That can be checked by means of whether this buttrell is having that much strength, shear strength. So again, same formula we are going to use. Area multiplied by stress is equal to force. So as already we have decided that the P is the tensile force which is applied. Now shearing is occur for this rectangle. Okay. Now this rectangle dimension can be calculated as A is this remaining part, this part inside the sprocket. Okay. After the quarter joint, whatever may be the length which is remaining inside the sprocket, that you have decided as A. That's why this rectangle has a length equal to A. And what will be its depth? Its depth will be equal to the diameter of this pivot. Am I right? So this will be D2. This will be A. So A multiplied by D2 will become this red area. So A multiplied by D2 is going to become this red area. But shearing is occurring not only to the one side, it is occurring to the both sides. That's why this 2 is used, because this area is of area of one side of this rectangle. To the other side also we are going to have same area which is going to shear. So we have used this 2 as a symbol or whatever, that multiplication of this area, because 2 areas are there. That's why we are going to use this 2. So this 2 multiplied by A multiplied by D2. A is the length, D2 is the depth. So A multiplied by D2 is going to become this red area. As 2 areas are there, that's why 2. Multiplied by shear strength, that is tau. Now how to calculate this value of tau? That is again calculated by means of SYT. SYT divided by factor of safety, that you have calculated as tensile strength. Now this tensile strength is exactly not, but somewhat rough intimation is given as the shear strength is the half of that tensile strength, or tensile strength is double of the shear strength. That's why we are going to say that this tau is calculated by means of same sigma t. Sigma t divided by 2 is value of tau, and that value is taken for the calculation here, and we can calculate the dimension, that is A as well as D2. And already if we have calculated this A and D2 in case of this tensile stress. Okay, here we have calculated it. D2 we have calculated, as well as A we have calculated from the empirical formulae. So what we can do with this formulae? With this formulae you can check whether this tau is within limit or not. That is the shear stress value which you are going to find out from this formula. This shear stress value is exactly the value of allowable shear stress. And if it is so, then we can say these dimensions which we have find out are within the safer limit. And hence, this Piggott dimensions, whatever maybe we have calculated from these formulas, are safe. Getting main important thing is that we have to consider tensile load, and later on this crushing load or crushing stress and shear stress are considered, and they are checked whether they are within the limit or not. Getting so all these entire dimensions of this Piggott are calculated or find out, and later on we are going for the designing of pocket. Okay, now this pocket is designed and our dimensions of that pocket are calculated, okay, by considering the same thing and by considering the same type of load. So we will see this thing to the next lecture. Today we will stop here. Okay. Before we close our session, let me know, do you have any question? Anybody of you?
Sir,
Yes.
sir, numerical is going to be there in university exam, na?
Right.
This
We will
topic.
have, yeah. There are two types of questions. One is you have to elaborate the steps. Okay, you have to write the design procedure for the quarter joint. In that design procedure also, you have to write all the formulas. Am I right? And second type of question is that numerical will be given based on this quarter joint. Various dimensions or the various parameters are given, and you have to calculate the dimensions of this quarter joint. Next. Anybody else? Hello?
No, sir.
हॅलो सर हॅलो
Yeah. More.
सर इम्पिरिकल रिलेशन जरा सांगा की समज
Empirical
ते
relationship.
आपण
Here.
ते D3 इज इक्वल टू 1.5 इंटू 1.5 ते फिक्स कसं व्हॅल्यू म्हणजे समजलं नाही
हा.
फिक्स आहे का
आता
ते
ते सांगतो आता. मी सगळ्यात सुरुवातीला हे म्हटलं होतं की एकदा तुम्ही त्या रॉडचा डायमीटर फाइंड केला की त्याच्यावरून आपण म्हणजे प्रिव्हियस एक्सपिरियन्स वरनं काही रिलेशनशिप डेव्हलप केलेले आहेत, ज्याला आपण इम्पिरिकल रिलेशन म्हणतो. आता हे 1.5 जे आहे ते 1.5 हे तसंच एक कॉन्स्टंट डिसाईड केलाय. त्याच्यामध्ये फक्त एक्सपिरियन्स हे लॉजिक आहे. जसं तुम्ही मशीन ड्रॉइंग मध्ये असेंब्ली आणि डिटेल्सला कुठलं वापरलं होतं, कुठला तुम्ही कंपोनंट घेतला होता, त्याच्यामध्ये काय काय व्हॅल्यू आहेत. जसं की तुम्ही नट अँड बोल्टचं ड्रॉइंग काढताना जर नट डायमीटर डी असेल तर त्याच्या हेक्झॅगॉनल हेडचं डायमेन्शन किती असतं 1.2 डी, त्याचा थिकनेस 0.5 डी असतो. ओके, म्हणजे हे जे आहे हे इम्पिरिकल रिलेशन आहे. मोरे
हा
समजले?
हा.
ओके. एनी अदर क्वेश्चन? Anybody else? Any question? Hello?
No, sir.
No, sir. No, sir.
Okay, no problem. I will take present now.